continuing our discussion of Muppet model optimization, and today we're talking about quantization. So these models are pretty darn big, and one thing that you might ask is, we're storing the parameters of these models as full precision floating point numbers. Do we need to do this? You might want to quantize the models, lose some precision, and have a much smaller model. It could take up less space. If each individual parameter is smaller, you might be able to do inference faster, and you might also be able to save some energy. That means that not only are you protecting the environment, but maybe you could also run it on devices with a tiny battery like a cell phone. And this could also mean that you could deploy it on more devices that maybe don't have GPUs, like a cell phone. But there are reasons why you might not want to quantize. First off, you're going to lose some accuracy. It's unavoidable. If you take a model that was trained with full precision and turn it into something that doesn't have full precision, you're going to get some stuff wrong that you didn't get wrong before. And these mistakes are going to not be uniformly distributed. They're going to appear in some parts of your model more than others. And this will work better on some devices than others. If you have access to a bunch of great GPUs, quantization is not going to help you as much. And quantization makes your life harder. You're going to have new code, handle new hardware. You may not want to do that. So there are pluses and minuses for quantization, but a lot of the models that you use, especially on your cell phone, have been quantized, and the only reasons that they work on your cell phone is because they have been quantized. Someone put the effort into making sure these techniques worked for your device. So here are some examples of the benefits of quantization from Meta talking about their Llama model. You can use only 25% of the memory that you were using before and be 2 to 4 times faster. And that's pretty good, with a reasonable degradation in quality. Now, there are two main buckets of quantization that we could talk about. One is you still have a floating point number, sine, the exponent, mantissa, all the things that you learned about from the IEEE standard, and you just use fewer bits. You have a smaller range, reduced precision. This is a relatively straightforward process to go from float 32 to float 16, say. What is a little bit more interesting is going to an integer. So we're going to map the floating point number to, say, an 8-bit integer. This requires a little bit more math, so we'll talk about this in more detail. So this is often called an affine quantization, where we're going to take the range of floating point numbers and map them into the range of integers, and we're going to do so with this equation. So if we have some x, the original floating point value that we want to represent, we need to transform an integer xq into that x, and we're going to do that by scaling it by s, that basically represents the range of the original floating point numbers. And this is where we can be a little bit smart. When you're talking about the weights of one of these Muppet models, there is a relatively limited range of weights, partially because of regularization, that you will see, and you can represent that range a little bit smartly, explicitly in this parameter, like what is the min, what is the max, and that range should cover the min and max. You then have the quantized integer. That's the integer representation that will turn into xq, and you subtract off z. And so z here in this transformation is very important because this is basically the integer that represents 0 in this mapping. And it's very important that the floating point 0 gets mapped to one specific integer. you don't want to miss 0 in your mapping because, as you know very well, linear algebra doesn't work without 0, so you want to make sure that 0 is in your mapping. So this basically makes sure that z is in the integers. So if we have 8-bit numbers, the XQs go from -128 to 127. Our S's maybe represent the range from -1 to 1 or -10 to 10, something like that, not too big. And again, z is an integer. So let's see an example of this. So let's say that we're mapping -1 to 2. The integers range from -128 to 127. Given this range, our S needs to be something like 0.01. So we have 3 over something a little bit less than 300, so it makes sense that's a little bit more than a hundredth. So if we compute the 0 point, this means that -43 is the representation for 0 in the scheme. Okay, so let's do the forward mapping. Let's say that we have -0.8. We want to represent that as an integer. Okay, so we have -0.8 divided by 100th, and so we have about -50 minus about -50. We get something around -100. And so if we now map 0.5, then we do 0.5 divided by 100th. That's around 50. So when you subtract off something around 50, we get -1. And then 1.5, we're going to get a larger number that maps to around 85. This is how you do the mapping in broad strokes, but as always, the devil is in the details. And this is an area of active research. And the issue is you have to quantize multiple parts of your model. You can't just quantize one bit. Like, there are a lot of parameters that could be quantized if you want to save space. But the error propagates. And so you basically need to choose a quantization that minimizes the overall error of your model. And you can't do this all at once. That would be too complicated. So you basically need to go through your model and figure out, okay, I'm going to quantize this in this way. And then after I do that, I'm going to quantize this other layer. And so you need to figure out a strategy to do that quantization. But this isn't independent of your data. This really depends on your data. So you basically need to do this in expectation over the kinds of data that you're likely to see, and the order matters. So you need to figure out how to quantize your data, looking at the individual layers and figuring out what is the optimal way to quantize my model. Okay, so to wrap up, modern models are big. That's no surprise. But quantization lets you run them on smaller computers or phones than you would otherwise. And while it does degrade the quality, you can do it strategically to minimize the errors that you get after you do the quantization.
Thanks for watching this video. I picked out another video that you could watch up here. If you want to get more context for the videos, check out this link or the link in the description. It gives you readings, programming assignments, and other things that might be more helpful. Finally, help me out and help other people find this content by providing a big gradient to the recommendation algorithm. Like the video, subscribe, or leave a comment down below with mistakes that I've made, newer research that has come out, or just tell me about where you are in your journey.